All right. So let's start with an nth order differential operator, which is elliptic, and just for the sake of, well, yeah, let's just assume that M is compact with boundary. So, I mean, we talked about the check space. So this is just gamma acting on the maximal domain. And it is isomorphic to dom d max mod our dom d min. So this is what we've seen so far. Now, the first kind of thing we can wish for is as follows, right? So suppose, so we know that, I mean, I've already talked about the collar neighborhood theorem. So we know that there exists a U, which is an open set with the boundary contained in this open set such that U is diffeomorphic. Well, U is, well, there's a diffeomorphism to 0, 1 across the boundary, which is a diffeo. Well, what can we hope for? So we know that there's this nice collar neighborhood around the boundary, and typically, you know, when we want to consider canonical operators, it would be somehow coming from this collar neighborhood. So the kind of thing we can ask for is, you know, well, suppose, I mean, actually for what I'm about to say, it doesn't matter that there is a collar neighborhood. Suppose that d tilde is another operator. So d tilde is again a differential operator which is order M, E, F, elliptic. Actually, let me erase this for the moment because the collar neighborhood actually doesn't come into play in what I'm about to say. So suppose that there exists. Yeah. Let me restart this. So suppose there exists a different. So suppose D is another differential operator of order M. That's elliptic. And let U be a neighborhood. So this is an open set which contains the boundary, such that D restricted to this neighborhood is equal to my original operator restricted to U. Okay, so certainly we can ask that. So what this really means is that if we're looking inside some chart, that everything is equal, right? So inside this neighborhood. So then the question one can ask is H check D tilde equal to H check of D. So certainly this is true. And you can prove this, right? So this is true. And maybe I'll let you think about how to prove it, but the way to do it is to really institute a cutoff function near inside this neighborhood that's equal to 1 and 0, or maybe enlarging the neighborhood a little bit, or finding a smaller neighborhood of U, and then instituting a cutoff, and then you can control things using this cutoff to assert that this is true. So at least in this very simple situation, we can see how we can now understand the operator D in terms of another operator D tilde, as long as they're equal near the boundary. Okay, and that's what we would expect in terms of boundary value problems. But maybe we want to go further, right? And this is where I want to bring in the collar neighborhood. So suppose, so we know there exists a U in M with the boundary contained in U and U being diffeomorphic. This is what I wanted to say before. I jumped the gun a bit. This is a diffeo. And maybe we can find that a d tilde that looks like this. So this is dt plus some a, where a is now, say, an order m differential operator on the boundary, mapping from E to F. Well, okay, maybe mapping from E to E, and then maybe I can put a symbol here, some sigma t. All right, so this is this is an endomorphism that takes me to the bundle F. So in this situation, it looks like we have a simpler operator, and the point is that d tilde might not be equal to d on anywhere, anywhere. And then maybe the point is that we want to now understand the check space. So in this situation, it's not straightforward. So this is not straightforward that h check of d tilde would be equal to h check of d. Because we don't have this nice control. We don't have this way of equating the two operators, so we can't just hit it with a cutoff, right? The difference between the operator d and d tilde could still be operators of order 0. It could be that, the operator d tilde and d, their principal symbols are equal on the boundary. But that still doesn't guarantee that they're going to be equal in some neighborhood. So this is sort of what I was really trying to get at last time, right? I don't want to spend too much time on this, but this is really what I was trying to get at. So a concrete example of this might be as follows. So suppose that we're on the half space. So suppose that M is the half space, and we have maybe an operator which looks like this is alpha equal to M, A alpha d on dm dx alpha of u, plus now we have some lower order term b of u. So the model operator, or the canonical operator we might want to consider in this situation, might be just this operator here. And you see, now there is a lower order term, potential lower order term involving lower derivatives, that's not present in this operator. And this operator is this is a simpler operator, right? So if we were able to say, so if h check of d is equal to h check of d canonical, then what this is really saying is that we can understand boundary value problems of a more complicated operator d by a simpler operator, model operator. And this is I cannot give you an answer to this in the general order case. I haven't really thought about it, and I cannot really give you a good answer in the general order setting of how to do this. So maybe that's something you can think about. But this will really be something we're concerned with in the first order setting. Okay, so this is all I will now say about general order problems, and from here on, I'm going to focus the attention of the subject on first order operators. Okay, so first order elliptic operators. Okay, so throughout mu is a measured manifold with a compact boundary. Okay, so this is the notation we're going to fix. So maybe I'll put this in a list or something. So 1, The second point is that we're going to fix some interior pointing vector field. And EF, so EHE, FHF are bundles which are Hermitian. And the fourth thing is I'm going to assume that D is a order 1 differential operator EF elliptic. Okay, so this is going to be the background assumptions for us from here on. Okay. So we've already seen now the Collar neighborhood theorem, and the Collar neighborhood theorem is just it's a topological theorem. It tells us that topologically we can unfold a neighborhood of the boundary to just a half space involving the boundary in some sense. But what we want is we want something that also encodes some geometric information. Okay, so lemma. So it's a geometric reduction lemma. So there exists a unique vector field, T, covector field, sorry, on the boundary such that the tangent bundle on the boundary is in the kernel of this vector field, okay, and T of T is equal to 1. Okay, so full stop. So that's the first assertion. In a neighborhood, U of M with, in an open neighborhood. In open neighborhood, U of M with the boundary contained in U. There exists an R, so there exists an open neighborhood. There exists an R, and there exists a map that takes us so T little psi, so this is equal to T little psi, that takes us from U to the cylinder 0R, which, well, maybe I'll just write R here actually, which we define to be 0R across the boundary, such that the following hold. So the first point is that the boundary is obtained as T inverse of 0. Second point is that this map psi restricted to the boundary is equal to just the identity map on the boundary. The third point is that the differential of this map acting on T is equal to dt along the boundary. T is equal to dt along the boundary. sorry, tau is equal to dt. And lastly, if I take the measure and I push forward the measure, this is equal to just dt tensor. So remember, nu is the induced measure on the boundary. Okay. Okay. So the existence of this covector field satisfying this condition, so the existence and uniqueness of tau, well, this is just a pointwise exercise. Okay, so I'll omit that. So let's prove the rest of the theorem. So for the rest, this is the procedure. So we can extend, so we extend T to some open neighborhood U0 of the boundary, say T tilde, right? So we call it T tilde. So this is a non-zero extension. Well, okay, maybe this is the wrong way to say it. I should reverse the order of this. Okay, to T tilde non-zero in some open neighborhood. Okay. Now we are going to solve for a function f, possibly in a smaller neighborhood, into R, certainly still containing the boundary. Such that, so we want it to be divergence free when we multiply by this vector field T tilde. So what's this? This is going to be df of T tilde plus f div mu T tilde. And we want, of course, we want to give it an initial condition. We want to be equal to 1 on the boundary. Okay. So this is an ODE. So this is an ODE along integral curves of T tilde. So that guarantees us the unique f. But of course, I mean, I've written the divergence here with respect to mu, so how do we make sense of that? Well, you can use the fact, so for divergence, use the fact that there exists Riemannian G induced by mu and t such that the volume measure with respect to G is equal to d mu, and write div mu equals div G. Okay, so I'm sweeping a few of these details under the carpet, but that's how we would obtain the existence of that. And I'll remark on why we need this f in a second. Okay, so now let's take the flow. Okay, so let phi tilde be the flow associated to T tilde. So the fact that this is compact implies there exists this R positive and say U2 open with the boundary in U2 such that ZR maps to U2, which is TX mapping to, so this is now the flow, so I've called it the tilde. It's not the capital psi, no, it's capital psi tilde, right? Sorry, it's just up here, capital psi tilde, so maybe. So there's tilde up here, right? So this is the flow is the psi tilde, okay? So because by the compactness we have some R such that this is a diffeo, right? So possibly we might need to shrink the neighborhood U again, right? So we obtain U2. Okay, so now we set the phi equal to exactly the tilde inverse. And so by construction, obtain 1 to 4. Okay. So why did we go through, I mean, here we haven't, why did we bother with this F? So the point is that we want the F. So, okay, so let me see. I mucked up a bit here. I think this is the, sorry, this is the flow associated to F tilde, right? F times tilde. So where did the F come in? The F comes in, F was used to ensure that div mu of Ft tilde equals 0, and that's what gives rise to 5, right? That's what gives rise to the fact that the measures can be nicely equated in this way. The push forward of the measure is exactly what we want. Okay. So anyway, what this is really telling us, so it tells us that we start with manifold with boundary, and then in some neighborhood, maybe I'll make this a little wilder. So it's telling us now that there's this neighborhood and this neighborhood is, so this is my U, and then it's telling us that, you know, I mean my T might look, so maybe I'll draw my T in a different color, so it might look sort of like this, but now my T here is as if I have a product type metric. Okay, so it's really a deformation that really takes into account the inward pointing vector field, because we don't have a metric here. We have no notion of, you know, things being normal and so on and so forth. So we have to ensure that we correct things in a way that, you know, we can find a neighborhood where everything fits in nice and snug and in a product-like form. And I guess that's why, you know, I called it the geometric reduction. Okay, so now the point is that we can examine our operator inside this cylinder. Okay. But before we do that, let me just remark on something. So by ellipticity, right? So let's examine the operator. So by ellipticity, we can find a unique connection that depends on the operator D on E, such that if we take, so maybe I shouldn't say in, I should say in U, which is, as we wrote before, this is isomorphic to partial M is equal to ZR. Okay, so here we have some EI, and I'm going to let EN equal partial T, okay? And so du of X, I'm going to write as equal to I equals 1 to N of dx EI. So actually this expression that I'm writing here is not dependent on us being inside this cylinder, right? So the expression I'm just about to write, namely this, is not dependent on being inside the cylinder. So this is true everywhere if you start with, say, some frame. However, I want to equate, En equals to partial T. So this is the vector field, this is the vector field partial T, or it's push forward. So in order to do that, I of course have to be inside this cylindrical, this neighborhood where I can make the right identifications. Okay, so in having said that, so what do we end up with? So now we end up with I equals 1 to N minus 1 dx EI dEI ux plus, now I have I equals 1 to N minus 1 partial dx dt. Okay, maybe I need to move. I need to make some more room. Oops. N minus 1. Actually, I have no sum here, so what am I doing? No sum here. This is partial t of u at x. Okay, good. So now what am I going to do? So I'm elliptic. So my operator is elliptic, which means that these symbols are invertible. So let me do that. Let me pull out this symbol here, right? So I'm gonna do a couple of things. I'm gonna first, okay, so let me do it in steps. So first let me pull out dx dt. So now I end up with I equals 1 to N minus 1 dx dt inverse composed with dx EI nabla dEI u of x plus, now I have this term here. Okay, but I'm still not happy with that. I'm going to do one more thing. So let me, I know this is an excruciating detail that I'm giving you this. So dx dt inverse composed with dx EI nabla dEI u x. So now I'm going to add a term here, which is going to be the d partial t of u x, d partial t of u, d partial t minus dt of u of u at x plus, now well, maybe I should have written this right out the front, right? So let me take this here and write dt plus. Okay, so the first thing is that let's just note that this is a zeroth order term, right? Because I have dt and I'm subtracting. So you can write this out, this connection out in detail, and you can see that the difference between these two is a zeroth order term. So that's good. That's why I've written the u out the front here. I haven't written this acting on u because this is, of course, then a multiplication operator, right? So that's the first thing. So maybe I'll write these things in yellow. Okay, so this is a zeroth order operator. Yes. So the question was, shouldn't the dt in front get a u? Absolutely. And it should be u at x. So I'm out of room here. At x plus. Of course, the u depends on both x and t, right? So, but I'm just really writing the x dependency here. So first of all, this is a zeroth order operator. The other thing is, I mean, the symbol here, this is mapping from ex to fx. So the inverse symbol, this maps fx back to ex. So together, this is a map ex to ex. Okay, yeah, it's a bit annoying that I don't have enough room here to write these things. Let me move this down a bit further. And write the ei here. So I want to write something. I want to write something more. The point is that this is now. So if I look at this whole thing here, this is what? This is an elliptic. So this is a symbol, and this is an elliptic. Order 1 operator on the boundary. It's purely an operator on the boundary, right? So this is differentiating the t direction into here. So this is differentiating the direction here this way, and we now have an operator which acts just on these slices. Okay, so that's good. So it's an operator of that form plus a zeroth order term, right? That's what we've determined. And this is a very important gadget. So this class of operators are very, very important because these operators, we have a lot of choice of these operators, right? We can add zeroth order terms and we end up getting lots of these kind of operators and they don't alter the problem, right? We can add, subtract things and, you know, we can just try and think about just operators and these operators, I mean, the important fact about them is really their principal symbol, which takes this form. So let's highlight that, right? So this is a very important class of operators. So definition, an operator A, which is a differential operator of order 1, on the boundary, taking values in E, or maybe you can write E restricted to the boundary, is called an adapted operator to D if its principal symbol satisfies AX psi is equal to dx dt inverse composed with dx psi. Well, actually now we're really on, so I should say that now we're on the manifold, right? On the boundary. So the dt is a tau, right? So for psi in Tx, the cotangent space of the boundary. Okay, good. So clearly, so maybe I'll write remark. clearly A is elliptic. Okay, so this principal symbol is a composition of the principal symbols built out of an elliptic operator, so the principal symbol is surely invertible. Okay. So why do I want this? So remember the picture that I told you, that what we would really like to be able to do is to understand a more complicated operator in terms of a simpler operator. And it would be even better if this simpler operator is somehow constructed from boundary data alone. Okay, so that's the picture that we have. We have an operator on the boundary satisfying a certain condition, which induces an operator on this cylindrical part to the interior. And we want that operator to somehow give us all the information about the more complicated operator that we have. Of course, we have to have some certain constraints on the operator on the boundary, right? And that constraint is precisely the adapted operator. So, I mean, of course, we need to make this precise. So the first was a geometric reduction. The second is an operator reduction, right? So we have, on the one hand, we have geometry, and then this has to somehow be reflected in the operator, because we're dealing with things like maximal domains of operators and so on and so forth. So we need to know that we can make certain, we can equate certain things, and we can make certain identifications. So on the one hand, we have to sort of have the geometric details, and on the other hand, we have to have the operator theoretic details. Okay, so let a tilde be adapted operators for D and D tilde respectively. So you're given these operators, right? We're not extracting them in some way. We're just, so the calculation that I did earlier was just to arrive at the right principal symbol condition. But now we're saying, you know, just give me A and A tilde, which are adapted operators for the boundary. Clearly, with the expression that I wrote before, they exist. But here they can be any adapted operators. Okay. Then there exists differential operators. So there exist. So then maybe I'll write it in words. There exists. Exist. RT, which is a differential operator of order 1 on E, and RT tilde, which is a differential operator of at most order 1 now, right? I'm not saying that they are order 1, they are at most order 1. Remember, that's what the diff 1 stands for. So, at most order 1. On the cylinder ZR, varying smoothly in T in the range 0 to R, such that inside U, or which is equal to ZR, D, so I'll write D is equal to sigma T partial T plus A plus RT, and D tilde is equal to sigma minus T star partial T plus A tilde plus RT tilde. Okay. And so this is the most important part, because we need an estimate, right? If we want to somehow reduce the operators from one to another, we need an estimate. So there exists some constant, a finite constant, such that RT of U can be controlled on L2 of M against a constant. I'll tell you that in a second. So the question is, what is the sigma T? Well, okay, maybe I should just tell you that now. We don't just state existence. What do you mean? Okay, so let me move this. So where sigma T is equal to dx dt. Okay, I wanted to just make it a bit simpler. Okay, so anyway, let's get back to the estimate. So remember, I mean, you know, when we wrote the expression for D before, we had this symbol term out the front, right? So these are operators on this. These are operators purely on the bundle E, but D is an operator that maps from E to F. So the sigma T is the part that takes care of that. Okay. Anyway, so and we have RT of U being controlled in the following way. So this is controlled in T against AT of U, L2 sigma M, plus, of course, you know, we expect this sort of an estimate to be inhomogeneous. And we have similar control on the RT tilde of U. Now, with respect to A tilde. So the existence is of the operators. So let me just remark on this. So the existence is of the operators RT. We're given some A, and we obtain some RT such that this estimate holds. Okay, that's what it's saying. Now, of course, the constant here then depends on A and on this neighborhood and all of the data that we've included so far. Okay, but that's not so important. Okay, so this is a very important lemma because it tells us, so, you know, if you want to geometrically think about the problem, you can think about these operators A as being something like nice coordinates. And it's saying that we can somehow deform our operator or write our operator in this nice form, and the error term that we get, which is exactly these RT, these are the remainder terms. These remainder terms can be controlled in some nice way against the operator A. And the operator A is given, right? That's arbitrary. It just has to be an adapted operator. So it just has to satisfy the symbol condition that we wrote down before. Okay, so let's consider the proof of this because I think it's instructive. So as we have already seen, so I'm going to just prove this for prove only for A and RT since A tilde, RT tilde similar. Okay. Sorry, I'm really sorry. That's really bad on my part. I don't mean D tilde, I mean the formal adjoint. Yeah. Thank you so much for asking that because that would have been quite confusing. The A is an adapted operator for D, and the A tilde is an adapted operator for D dagger. Now, I don't write A dagger there because A dagger already would have a meaning. So that's why I'm writing A tilde. Okay. All right. So let's think about the proof. So as we have already seen, So what have we already seen? We've already seen that we can write this as partial t plus some, say, xt, right? So we've already written this out. So this was the instructive calculation that we wrote down before. So certainly we have an expression of this form. And also we have, and clearly, the principal symbol of x naught at x psi is precisely equal to the principal symbol of the A. Okay? So now define, so this lemma is really just the obvious, you just do the obvious things, right? You just do all the things that are completely obvious. Okay, so you define the RT as simply being equal to xt minus this operator A. And so that gives us that R0 is of order 0 because they both have the same principal condition, principal symbol, xt and both A. So that means that at 0, the principal symbols cancel out, so it's an order 0 operator. Okay. So since RT, so it's clear that RT is in diff 1. So this is in diff 1 of E restricted to partial M. Locally, what can we do? So RT of U is going to be something like I R T I partial I of U plus I don't know, some term, say ST of U, which is a lower order term, right? So locally we can write it like this. And so if I subtract now from RT, if I subtract R0 and act on U, so this is going to be equal to I RTI minus R0I of partial I of U plus ST minus S0 of U. Okay, good. So let me just estimate it now then. So RT minus R0 absolute value. So this is going to be less than or equal to so what do we have here? So we have that this is now going to be what's the nicest way to estimate this? Okay, so this is now going to be less than or equal to, by the triangle inequality, RTI minus R0I partial, well, okay, so yeah, that's the best way to do this. Let me see. Okay, maybe I won't write this at first. Let me note the following, right? So T maps to RT are clearly smooth. And in particular, that means that T maps to RT is actually Lipschitz. And also T maps to ST is Lipschitz, trivially, right? So this is RT and T maps to ST smooth. So these two things imply this, okay? So that means that RT of I minus R0 of I acting on some V. So we have some constant and this is going to be bounded by T against V, okay? Because it's Lipschitz in the line direction. Yes? Just by coefficients. I mean, just think of coefficients, right? It's the obvious thing. So here we have coefficient. Yes, so put the RIs in there. Maybe that's the easiest way to do it. So So this is certainly true, right? For each I, we get a constant such that this is true, and we get that st, well, sorry, we don't have si here, right? So so yeah, they are as operators because, of course, this is still a coefficients, right? These are a matrix here. So sorry, so this is a matrix. So when I'm talking about smoothness, I'm always meaning in terms of coefficients. Okay, so this is now going to be, of course, bounded by, again, T of V. Okay, so why do I want to write it in this way? So then it means that when I write out the difference, RT minus R naught of U, so this is now going to be, you know, bounded by some T against, so now there's going to be a sum, I equals 1 to n, say, of partial I of U squared plus, okay, so now I'm going to have plus U squared. Okay, so this is what we end up with when we combine these two estimates. And then we take, I don't know, we take an absolute value and a sum, and then we majorize it in this way. Okay, so what does that tell us? So that tells us now, so this calculation was local, but everything is compact here, right? The boundary is compact. So therefore we can just patch together to obtain that, so by patching, we obtain that, well, using compactness of the boundary, we obtain that RT minus R naught of U is, so we just, by patching using compactness and just integrating this expression, right? Integrating this expression, we obtain that this is now going to be controlled by the Sobolev norm, the H1 norm on the boundary, right? So I should write L2 here. So this is L2 on the boundary, and this is the Sobolev norm on the boundary. Okay, that's good. But now the point is that this is the difference of two operators that we bound in this way. So by the triangle inequality again, this gives us that RT of U is bounded by T norm H1 partial M plus R0 of U. But R0 of U is an order of, it's an operator of order 0, so it's just a bounded operator, right? So this is now going to give us perhaps another bound, U H1 partial M plus norm U. So this is where the inhomogeneous term comes in. Okay, so what? But now the point is that the operator A is an elliptic operator of order 1 on a compact manifold without boundary, right? The boundary is a boundaryless compact manifold. So that means that we can control the H1 norm by A of U, L2, plus norm U, L2. So this is again L2, right? Sorry, this is L2, this is L2. Plus, of course, we still have this norm U in L2. But of course the number R is finite, so for the inhomogeneous part we can just, you know, write R in place of T, and then we end up with the required estimate. A of U L2 of partial M plus norm U L2 of partial M. Okay, so that's the theorem. No, that's the lemma. That's the end of the lemma. Okay, good. So the moral of the story is, you know, in this situation, the remainder terms that we get, we can control in terms of the operator that we want to compute things with respect to. Okay? So, all right. Okay, so what do I want to say next? So, following on from this, maybe I would take the time now to make a definition. Okay, so the model operator, what we call the model operator on the interval ZR, that was the notation I used, is precisely the operator D naught, which is equal to sigma naught. So I want to fix just, so remember we had this operator sigma naught was this is equal to the symbol, the inverse of the sorry, not the inverse, the symbol in the covector field direction tau, right? So I'll just write that out in a second. So the operator I want to consider is this. So this is a very simple operator now, right? We have a very simple t derivative here, and we have an operator A. So this is a model operator given. So this is really given as a given adapted A. And of course we can consider so this induces adapted operator and adapted for D, which is given, which is simply what? Which is the operator, let's say, so how would it look? So if I take the adjoint of this, it'll be sigma naught. So if I take the adjoint, things flip around. So this is going to be sigma naught A star sigma naught inverse, right? That's what it's going to look like. So this is going to be, sorry, there's a negative sign here too. Okay. So this is going to be an adapted operator for D. So why does this happen? So if we take, D formal adjoint, well then this is going to be equal to dt, negative dt plus A star and the adjoint here, and then of course we want to, yes? No, this is an adapted operator for D, right? This, so, sorry, this induces an adapted operator for D dagger, given by that, okay? So maybe I'll so A tilde equal to this, right? So given an adapted operator A, where we can look at a model operator, this induces an adapted operator for D dagger. And how do we come across this adapted operator? Well, we'll just take the formal adjoint of D naught. If we take the formal adjoint of D naught, we end up with this expression. And in order for us to write it now in the form that we wrote it before, we have to factor out the negative. So we get negative D naught, maybe put a star here, and then we have dt minus D naught inverse star A star, and then we absorb the D naught star here, right? And that's what we end up with. So the point here is that this symbol D naught star commutes with the dt. Okay? So so I should say where we recall this is equal to x tau, which is an endomorphism ex to to fx for x on the boundary. Okay, so this is the tau here, right? So that's the point. Okay, so anyway, so let's just fix the notation here. So why do we do this? Right? So why do we do this? We do this because later, so we won't do this right now, we reduce questions about no, it's a computation. I mean, we have operator d naught on ZR, and then we want to compute the formal adjoint of d naught, and the formal adjoint of d naught is computed to be this. Of course, you can write a dagger here, but I mean, it doesn't really matter, right? So if we compute the L2 adjoint of, well, if we compute the formal adjoint, this is what we end up with. So why do we do this? Because we want to later reduce questions about D and D tilde. Well, and I'll say questions about D because it follows for D tilde similarly to D naught. Okay, so why? Because we have D minus D naught now. This is going to be equal to dt plus A plus RT minus sigma naught dt plus A. And this is precisely equal to dt minus d naught inverse of the model operator d naught plus sigma t dt, sigma t rt, right? So this is just a simple calculation. So now we see that the model operator appears here, and this is the remainder part. And this is, as we saw in the lemma, controlled by A. Okay, we have a precise way of controlling this remainder term. So we will get back to this. We won't look at this right now, but I just want to, outline a roadmap of why we're doing all of this. The main point is that we can reduce the questions about D to D naught. So from now on, we're actually just going to consider the problem on the cylinder for the moment, right? But this is justifying why we can reduce questions about D to D naught. Of course, we haven't gone through and seen the precise estimates yet, but the thick and thin of it is that the difference between these operators take this kind of a form. So we want to be able to control D in terms of the D naught, right? And the justification is, well, it's a bit hand wavy, but the justification is this. Okay, so so just before we move on to the cylinder, let me just also highlight something, right? So a proposition at the level of generality. So before we had an integration by, we looked at the formal adjoint and we looked at the formula for the formal adjoint, right? Where we looked at sections that disappear, whose support disappears by the time it gets to the boundary. So let's instead now look at sections that don't disappear at the boundary and try and understand what they look like. So with respect to this symbol sigma naught, what we end up with is the following. DUV L2 MF minus U dv. So this proposition can be verified by just doing a local calculation, right? So this is equal to sigma naught u restricted to the boundary, v restricted to the boundary, L2 partial mf. Okay, so this is for compactly supported smooth sections that take a value at the boundary. Okay, so I just want to really remark that so the goal is that as we go along, we want to extend this. To d max and d max dagger, and we can see already from here where general perfect pairs enter the picture. The pairing at the boundary, i.e. right hand side term, equals is sigma naught u restricted to the boundary, v restricted to the boundary, L2 partial mf. I mean, this is the L2 inner product. Okay, so we have to, the problem that we have at hand is constrained by L2, the geometry of L2, right? So whatever we're doing, whatever we develop, whatever pairings that we explore between, you know, the check spaces and so on and so forth, all of that really hinges on everything being equal to the usual L2 inner product that we've already fixed, say on a nice dense subset, right? So for compactly supported smooth sections that take a value at the boundary. So right hand side term. Yes. Okay. Okay, good. So this is sort of what I wanted to say, and I wanted to also highlight here how for these general operators, at the boundary, the term that really appears is this term sigma naught. Okay? So one can do a direct calculation to verify this, but I mean, all of this, all of what we've done so far hints to us that really the model operator should really be the heart and soul of everything that we're doing or we're going to do, right? So, okay. So what have we obtained so far? So we've obtained so far, all of this hints at understanding A in diff 1e on the boundary such that the principal symbol of AXI is precisely dx tau composed with dx psi, right? So in particular elliptic. So, okay, so we have to obtain an understanding of such operators. So at this point, we have to make an excursion back into functional analytic or operator theoretic things, because to understand this operator A, that's what's required. Okay, so the next couple of lectures, so we've done some geometry up to this point, but we have to now get back to some abstract questions, right? So remember, when we talk about an operator, we don't assume that it's bounded. So this is just a linear mapping from B into itself. So, okay, so we say, so this is the definition of the resolvent set. And spectrum. So we say that zeta in the complex numbers, okay, so zeta in the complex numbers is a part of res t if z minus t is invertible. I.e., this is an injection, so it's an injective operator. The range is dense. Well, this acting on B is dense. Okay, so sorry. Dom of T dense. And there exists some constant such that, so of course we don't need the injective part here, right? I can just say it's dense range with the estimate zeta minus T of U, norm of U for all U in dom T. Okay, so we don't have to say that it's an injective operator. Obviously it's implied by the estimate. Okay, so the set resolvent T is called the resolvent set. And for zeta in res T, Z minus T inverse, which is a bounded operator now in B, is the resolvent. Is all a resolvent. Okay. Okay, so maybe I'll define just the resolvent here, and then we'll talk about the spectrum, right? So, well, okay, actually, yeah. So the spectrum is the complex plane subtract the resolvent. Okay? And there are three kinds of spectra. Okay, so we say that lambda is in spec P of T, so it's so this is the point spectrum. If lambda minus T fails to be injective. This is called a point spectrum. It's like an eigenvalue, okay? So it is in spec C, so this is the continuous spectrum. If lambda minus T is injective, dense range, but the operator lambda minus T inverse is unbounded. Okay? So this is the continuous spectrum. Okay. The last part of the classification is the last thing that can happen. So this is little r, so this is the residue spectrum. So if there exists a C such that lambda minus T U, so finite C such that it's bounded below by U, so it's an injection, but lambda minus T dom T is not dense. Okay, so these are the three types of spectra that can happen. Okay, so this is just to be informative. We're not going to be, I mean, we will have to be concerned with understanding these different kinds of spectra, but you know, it's more for being informative than anything. Okay, so I hope that this is just me recalling certain facts that you've already seen some spectral theory before, at least in finite dimensions. I mean, there you will not have continuous spectra or residue spectra. Everything will be point, and this will be just eigenvalues, and the spaces associated are the generalized eigenspaces. So proposition. So okay, so let's assume that we have a closed operator. Okay, so T is a closed operator. Then, so if T is closed, so maybe if T is closed, then what do we have? So the spectrum is closed. I.e. the resolvent is open then. Okay? But it could be the entire complex plane, right? Residue spectrum. So the last kind of spectrum is residue spectrum. Thank you. Sorry, I forgot that. So if we have non-empty spectrum, so if it's non-empty, if the spectrum is closed, then the resolvent set being non-empty means that, I mean, it's an open set in general, so it's a non-empty open set, implies that zeta maps to zeta minus T inverse is holomorphic. Okay, it's a very important result actually in operator theory. Third point, so if U mapping from B to B tilde is isomorphism of Banach spaces, then we have that the resolvent set of U inverse T of U. So now this is an operator on, obviously this is an operator on B prime. So this is equal to the resolvent set of T. And of course, the spectrum now also has to be the same. And so zeta minus U inverse T U inverse is going to be U zeta minus T inverse of U inverse. Okay. Okay. So I guess these statements can probably be found in Kato or Yoshida or whatever your favorite book is on the topic. Okay. So just in the remaining 5 minutes, let me just state another fact. So let's now assume that we have a reflexive, so we have a perfect pairing that's reflexive. So suppose that we have a reflexive space, a reflexive perfect pairing between spaces. Then if T is densely defined and closable, then we obtain that T star is densely defined and closable. It's closed actually. Okay, so the point is that before we saw that dense definedness is important for the existence of an adjoint, but of course the point was that the adjoint itself can be empty. It can be zero, right? It can be something quite trivial. So, but the point is that in a reflexive setting, if we have something that's densely defined and closable, then it means that the adjoint will also be densely defined, right? That's the main thing. It's not just going to be closed, but it's going to be densely defined. So it's going to be a non-trivial object, okay? Yes. It has to. No, T does not map from B1 to B2. T maps from B2 to B2. Okay, so I mean the adjoint is going to be on the other side of the equation, right? So okay, so maybe I need to, well, yeah, maybe I need to write this out a bit more clearly. So T maps from B2 to B2, densely defined and closable, implies T now, which, so the adjoint is going to be on the other side of the pairing, right? So this is now going to map from B1 to B1. This is densely defined and closed. So that's the that's the first. So I should say that's the first thing. The second thing is that the kernel of the adjoint is equal to the annihilator with respect to this pairing of the range, right? With respect to B1, B2. Oops, B1, B2. And the third point is that if B1 is equal to B2 is equal to H, which is the Hilbert space, then we have that H is equal to the kernel of T star plus the range of T closure, and this is equal to the kernel of T plus the range of T star closure. Okay? So the proof of one, well, I won't go through that, but it can be found in Cato, or maybe it should be an exercise. So the key here is, the point here is to consider canonical adjoint with respect to the pairing B2 star B2, and you know, we had this characterization, the inverse graph of T star canonical is equal to the graph of T annihilated, and use this to obtain the conclusion, right? So I didn't expect to get into that because actually I didn't even think I remembered how to prove it, but that's how you do it. Okay, so let me, okay, we only have 1 minute, so let me just quickly prove this. So the kernel of T star being contained in the range of T perp. So how does this go? Well, we have that if U is in the kernel of T star, then we have 0 equals T star UW, and this is equal to U TW, and this is for all U in DOM T star and all W in DOM, DOM T, yeah. So that tells us then that if we're in the range and we take U in the, so what's this telling us? It's telling us that if we annihilate the range of T, then we will end up, elements of the kernel of T star will be in the annihilator of the range of T, okay? And then the other direction, perp B1, B2. So for this, again, so this means that if we are, so this means that, okay, so U TW is 0 for all W if U is in this space range T adjoint, but then UTW, so 0 equals this is the same as T star of UW equals 0, but of course from item number 1, so this is in DOM T, we have that W is in DOM T dense in B2, and because it's dense, we conclude that T star of U equals 0, and that's the same thing as saying that the kernel, that U is in the kernel of T star. Okay, so that's the equality that we want, and this follows. So this I'll actually leave as an exercise, right? But it's an easy conclusion of putting these facts together.